Artificial Intelligence, Principles and Applications Lecture Number 7, Reasoning. This chapter discusses the various reasoning techniques in artificial intelligence. The mental ability found in humans, which is able to generate conclusions from assumptions or premises, can be termed as reasoning. In other words, it is amongst other things and means by which rational beings propose specific reasons, or explanations of cause and effect. In contrast to reason as an abstract noun, a reason is a consideration which explains or justifies. When we need a system to perform a task which has not been told, then the system needs to reason it. It must figure out what to do, from the knowledge it already has. We have already come across such examples of reasoning in previous chapters. For example, if we know parrots is a bird and all birds have wings, then we may ask, do parrots have wings? This is a simple example for reasoning. There are many situations where we need to answer the questions to get an inference. There are many types of reasoning methodology, which generate couple of knowledge in artificial intelligence. Abduction is the process of creating explanatory hypothesis. For example, when a doctor encounters a patient who has the same symptoms of someone whom he had treated before, may wonder whether the present condition is somewhat similar to that. Abduction is a reasoning process that tries to form reasonable explanations for abnormal observations and which is distinctly different from induction and deduction. MISIN, which is an expert system for medical diagnosis, certainty factors, truth maintenance systems, Bayesian belief networks, fuzzy logic and non-monotonic reasoning are some abduction systems. Scientists use deduction, who take a general scientific law and apply it to a certain case. The scientists are assuming that the law is true. Deduction can be used to test an induction by applying it. Although in the test cases, the initial theory is assumed to be true only temporarily. Inductive reasoning, or induction, is reasoning technique that forms from a specific case or cases and reaches a general rule. From observations, it draws inferences in order to make generalizations. Inference can be done in these stages. Difference between deduction, abduction and induction can be explained in a simple manner. Reasons from causes to effects is deduction, but reasons from effects to causes is abduction. Induction is reasons from specific cases to general rules. Figure gives differences between three reasoning rules. In this method of reasoning, for every situation an analogy of the similar one is taken into consideration. It then tries to create a mapping on the attributes of the analogical situation to the present problem. To use an analogy, these steps are involved. This reasoning shows causes and resulting effect. When we deal with a problem, it will show a set of causes and effects that are involved in it. It thus gives an understanding why a particular event happened or how this will happen if we move forward. This also draws an inevitable link between what happens first and what happens next. Comparative reasoning helps to find the importance of some attributes by comparing it with other. The gap size between the things compared indicates importance. If we compare against a high-grade attribute, then we feel ours as unimportant, and while comparing against a low grade will make our attribute look good. Conditional reasoning is based on if-then statements. For example, if we generate a reasoning based on if A then B, it means B will work only when the condition A is true. There is more scope as it opens door for situation in which what will happen if A is false. Because it is not explained whether B will be true or false when A is false. This reasoning system is highly useful when we design a rule-based system for a problem. These rules are forwarded from an expert's viewpoint. Criteria reasoning begins with defining the criteria from which the outcome of a particular decision is judged. The outcomes are then evaluated and the best criteria are selected. In logical arguments, it takes more time to establish a criterion, but in less logic situation, we assume the criteria and start working on it. Criteria which appeal to common values are likely to be easily accepted. Decompositional reasoning is the reasoning by which you break down the whole problem into small understandable parts. Then these small parts are analyzed and the conclusion is drawn on how they fit together. Finally, the conclusion on the whole matter is drawn. The use of examples in argument is the main use of exemplar reasoning. This reasoning may give a story or maybe a short comparator as an example. The duplication is possible in a situation or maybe a relatively distant metaphor for the reasoning. A known person, recognized situation or something not directly known to the other person is useful in exemplar reasoning. Modal logic describes the situations based on necessity and possibility. Also explore how they intertwine. The process is not carried out by stating the truth but by its likelihood. Thus, it uses words like can, may, should, ought, must, have to. Traditional logic was originated by Aristotle. It obeys formal rules and facts. It starts with premises that are assumed to be true, then uses only logical rationale to derive a conclusion. Pros versus cons reasoning seeks to weigh up the arguments for a case against the arguments against the case. A conclusion is arrived from the arguments that have checked whether the pros or cons were stronger. Thus, precipitating a reasonable conclusion is formed. Set-based reasoning is normally used in set theory. Its arguments range around whether things are members of named groups or not. For instance, a cat is an animal but not a vegetable. Systemic reasoning is a most generic approach. We can try to understand a case by considering the whole system. The various attributes are checked and analyzed. The relation between them is also validated. You can use the compositional scheme of reasoning to identify a case which does not belong to your consideration. During conversation we make many sentences and try to imply logical connection between them. But many a times the truth and logic that we assume will not be there. This is syllogistic reasoning. Bayesian reasoning based on a Bayesian network can overcome such problems using the probability principles. Bayesian networks are solid representation of probability distribution over a set of propositional arbitrary variables taking advantage of independence relationships. The non-monotonic reasoning is good because we can update the knowledge base by adding or deleting a belief as and when required. Also, we can use the existing knowledge to solve conflicts if there are contradictory facts. Motivation of the non-monotonic reasoning is to define a strong and flexible system to deal with situations of incomplete knowledge by considering syntax and semantic rules. These methods are not valid forms of inferencing, but they are important since they are being used in everyday activities. These are abductive inference, inductive inference, analogical inference. The idea of a truth maintenance system or TMS grew out of dependency-directed backtracking. A TMS may be employed to protect logical integrity of the conclusions of an inferring system. A TMS allows assertions to be connected via a spreadsheet-like network of dependencies. Assumption-based truth maintenance system or ATMS is a powerful tool for different applications in the domain of uncertain reasoning. ATMS keeps for each proposition a set of sets of assumptions under which the proposition is true. A proposition is believed at a given time if one of the assumption sets supporting it are satisfied. Justification-based truth maintenance system or JTMS keeps for each derived proposition a list of sets of propositions from which it was derived, and for each proposition, a list of propositions it supports. Fuzzy logic is a different approach to representing uncertainty in problem solving. Fuzzy logic focuses on describing events' ambiguities rather than the uncertainty about the occurrence of an event. Modification of the definitions of set theory and logic results in the fuzzy set theory. Traditional set theory defines set memberships as a Boolean predicate. In the usual set theory, an object is a member of a set or is not a member of the set. Traditional logics are based on the notion that PA is true if A is member of the set, otherwise PA is false. There is no parallel containment. This amounts to the use of a characteristics function for set A. Resolution by verification requires set of well-formed formulae be converted to clause forms, but a clause form may not exactly be resolving with clause forms may not give an answer which is required by the problem. So, one can deal with the well-formed formulae themselves and adopt methods of a given system called a rule-based system. In rule-based system, we have a set of fact and rules and a jail sentence. A set of rules forms a rule base and each rule can be used to produce a new fact from one or more established facts. The rule-based system represents knowledge in terms of a group of rules give a different situation. A rule-based system that consists of if-then rules, a group of facts and some interpreter controlling the application of the rules, given the facts. In backward chaining we start with the goal sentence, and the base rules are arrived at the given facts, whereas in forward chaining we start with the facts given in rule-based system to obtain goal sentence. Backward chaining architecture means that no rules are fired upon assertion of new knowledge. Consider this example for backward reasoning. If there are a cat and a dog, the cat is not afraid the dog. Solve the problem by backward reasoning. The solution is given in figure. In forward reasoning we obtain a sequence of assertions as inferences and two sentences are resolved. Forward chaining implies that upon assertion of new knowledge, all relevant inductive and deductive rules are fired exhaustively, effectively making all knowledge about the current state explicit within the state. Forward chaining may be regarded as progress from a known state or the original knowledge towards the goal states. Consider the facts and rules. Solve the following problem by forward chaining. The goal is to prove that there exists someone who is not a bulldog or who is noisy. The forward chaining is shown in figure. Case-based reasoning or CBR, as the name implies, is a reasoning based on cases. We may define CBR as the process of problem solving where the results are based on the solution of previous similar problems. For finding solution to a problem, solutions that were opted for similar cases in the past are retrieved. It is then used as a baseline for solving the present problem. The solution derived will be tested and retained. Case-based reasoning is a particular technique used for the development of a knowledge-based system. CBR compares a current situation, or case, with situations that have been encountered in the past to see if one or more of the earlier situations can provide a model for how to act in the current situation. For example, the multiplication of 12 by 13. CBR is well accepted in many cases because we can create solution from some background knowledge rather than from scratch. The users of CBR are lawyers, doctors, engineers, etc. The case base can be easily termed as a database of cases. A case is a contextualized piece of knowledge representing an experience. A case contains the past lesson, that is the content of the case, and context in which the lesson can be used. Typically for the CBR, the components are given here. Case-based reasoning can trace its roots to the field of psychology and theories about how human memory works. The case-based reasoning is shown in figure. There should be some method in which the cases need to be stored for easy retrieval. Most commonly used method is indexing. The indexing always needs to be predictive and must be concrete enough to be recognized in future. The cases are normally stored in a dynamic memory model, which helps to find the cases easily. When the match is found out, the system tries to use the same solution that is retrieved for this current problem too. The major task in CBR is to refine the result. As case-based reasoning suggests only the solution of previous matches, it is a hard task in validating the result. The correctness can be found out by applying the revisited solution in a real environment or in some simulation. Retaining is the process of storing or incorporating valuable knowledge that we have framed for future reuse. This is the final step in the CBR cycle. It can be considered as the feedback session where the system stores data according to the degree of success. The evolution of CBR is discussing here. These are the key features of the CBR system. If we see the practical point of view, the CBR is worked on situation-based. The cases are obtained on experience-based. Cases are covered situations which evolve over time or represent a snapshot at a particular moment. By combining both, cases are obtained. The uses like doctor, architect or judge did not simply depend on one situation. They have to refer cases under similar conditions and future outcome can be used again. Several features describing a problem by the case users plus an outcome or a solution. The ingredients of case are text, numbers, symbols, multimedia. Cases are records of real events and are excellent for justifying decisions. A case is a contextualized piece of knowledge representing an experience that teaches a lesson fundamental to achieving the goals of the reasoned. Case library should have as complete a set of examples as possible by start with a small subset and reached into solutions or outcomes. This is how case represented. Depend upon the domain, the cases can be represented differently. Cases can range from flat lists of features to reasoning processes using object orientation, semantic networks, or neural networks. Components of a case are description of the problem, description of the solution or outcome. The problem description has two types. Ones that are important in retrieval and ones that are not important in retrieval. Solution is the stated or derived to the problem specified in the problem description. The resulting state of the world when the solution was carried out is the outcome. There are many advantages while using the CBR for knowledge discovery. This is because it is derived from experiences. We need to keep in mind the various issues CBR can get through if a proper scheme is not being employed. The practical issues are given here. The databases and CBR are different. CBR support fuzzy queries and offers rich indexing support. CBR uses the known solutions to past experiences for solving a new problem whose solution is unknown. CBR combines the benefits of information retrieval and rule-based reasoning. By comparing CBR and rule-based systems, you may see these differences. The system becomes static unless new rules are added. It doesn't learn from new problems. While question and answer structure of RBS is restrictive. There are some disadvantages while using CBR. They are given here. There is a wide range of applications where CBR is being employed. In the case of medical field, CBR is most commonly used for diagnosis. For diagnosis, the system will try to retrieve a past case with the same symptom and nature. In financial market also, CBR is used to determine the values of variables by comparing with something similar. In applications of decision making and for creating new designs in architecture and industrial setup, we always check for similar cases. This reasoning refers to an inference method used in expert systems. Basically, model-based reasoning uses a model of the physical world. The main focus of application development is creating a model with observed data to derive conclusions such as a diagnosis or a prediction. The model-based reasoning schematic is shown in figure. You may please check the exercise in this chapter for understanding the improvements.